Subscribe now and click on the bell icon to never miss learning from Vedanti.
So now today we are going to the micro level, as in we go and see what if we look at the atom here. Atom has electrons going around it, and this is one thing we studied in the previous class also. So there is a magnetic dipole moment here, right? EVR/2. Does everybody remember this? Right? Does everybody remember what we did? Like EVR, that's a magnetic dipole moment. Now today what we are going to see is so the agenda today is go to the micro level and look at a collection of electrons, how they behave. So one electron will have this much of magnetic dipole moment, but what about the other electron? Is it going to add it up, subtract it, and what happens to a collection of electrons now? And then taking it further, what happens to a collection of atoms, right? So you start with one electron, you go to a collection of electron in the atom, so you have magnetic moment of the atom, and then you take a collection of atoms and see what happens. So this watch is collection of atoms. So what is the behavior on a macro level? So we will start from the micro level and go to the macro level based on that. Before we start that, let me ask you, have you understood the concepts that we covered so far? So let's get started here. Origin of magnetism and classification of material. So based on how these electron moments add up or subtract, the materials will behave differently. So as I said, we'll start with the micro today and go to the macro world and see what happens on a larger scale. Now every electron is revolving, right? It's orbiting around it. And then I don't know how much of quantum you have studied, but there is also a spin associated, and that spin is not a typical spin of like spinning of Earth. It's a completely different thingy. But to think of that, just leave it for now. So spin also would have contributed to some kind of dipole moment. So I'm not going very fast. I'll slow down here. Don't worry. So the total magnetic moment, so actually I'll create my own slide. So let's take an electron. Electron has some moment because of dipole moment is what we are talking about, right? So because of the orbiting around it, EVR/2. But then it also has some kind of moment which is going to be because of the spin, and that is a total dipole moment because of one electron. Okay, and this is what exactly this page is talking about. These moving electrons will have some kind of spin as well as orbital magnetic moment. So the electron movement is equal to orbital plus the spin. And just to let you know, spin contributes more compared to orbital. Orbital is tiny. Now same thing said again. No, but then I will cover that. Okay, so let's talk about an electron. Electron has some dipole moment, right? This part is clear to everybody, or is there some confusion? There is some dipole moment associated to every electron. But now let's take an atom as a whole, right? As a whole, maybe the electrons cancel out each other. The dipole moment of one electron is this way, the other one is this way. So they cancel out if they are equal and opposite. Or maybe there are not two electrons, there are 5 electrons. And then when you do vector addition of those 4, maybe in this case, the total magnetic moment is 0. So they might cancel out each other, right? So if they cancel out each other, let's say they cancel out each other. So can I not say the sum of the dipole moments of each electron is 0, right? In this case, this material is called diamagnetic. Okay. But then if you find a material where they don't add up to 0, right, so they don't add up to 0. Maybe there is some dipole moment still in there when you add that. So if you add these vectors, this is a net dipole magnetic moment, right? So this is not 0. This is called paramagnetic material. Rhythm, have you understood? Abhiraj, have you understood? Rukaiya, have you understood? Shivangi. Okay, I don't want to ask everybody individually. If it's not clear, please let me know so that I can revise that concept. Okay. Okay, so Rukaiya got it, Sai Kumar, Abhiraj, okay, cool. So this is what we're talking about here. If the dipole moment, total dipole moment of the atom, now look at the atomic level that we are talking about. We were talking of electron here, but then we are saying when we add up for one atom, if the dipole moment of the atom is 0, then it is diamagnetic, and we'll see the behavior because of that. But then if it is not adding up to 0, then it is called a paramagnet substance. They will behave differently based on this property itself. So now first let's start with diamagnetic substances, how they behave. When they behave, as in, let's say there is a magnetic field and then you put an atom there, how does that atom behave now? That's what we are talking about. So how do they behave in the presence of external electric field or magnetic field, sorry. Now, these substances, first of all, they are going to be repelled. So actually, I think I will cover that in one slide here. Diamagnetic materials are the ones where net of magnetic moment of the atom is 0. Right? For the atom as a whole, it is 0. The behavior-wise, it will be repelled. Example would be water. So it is going to be repelled by magnetic field. Right? So repulsion, not like this is some diamagnetic material you bring in the field here and it starts moving. It's so weak that you cannot observe. Observable at the observable level, it's almost negligible. Right? It's still there, as in the field lines will be repelled, but it's not observable. So that, and why does that happen? It happens because think about, there was some electrons which were orbiting that had dipole magnetic moment in this direction, and we are simplifying it. Let's say there were 2 dipole magnetic moments here, right? Now, when you have magnetic field here, this is going to reduce. This is going to reduce, and this is going to increase. Okay, and so the overall effect is going to be, and I think I have a slide for that. We can go to that slide. Yeah, look at this. Opposite, so electrons which are having magnetic moment in the opposite direction, they speed up, and the ones in the same direction slow down. As a result, there is a magnetic moment in the opposite direction of the field. Because it was all 0, that's why this happened. It was all 0. There were half of them in the direction of that, half of them opposite to that. So the ones in the opposite of that get stronger, and the ones in the direction of it get weaker. And that is why you will have a net result of the repulsion over there. Right? So please remember, dielectric materials will be weakly repelled by the magnet. Is that clear to everybody, please? Is that clear? Okay. Abhinaya says okay, clear. Okay. So again, the same thing, just to revise it over. So when there is an external magnetic field applied to diamagnetic substances, it develops a field opposite to the external field that we supplied, and there is going to be a repulsion in this case. Okay, so I think I will again summarize what we did so far. So diamagnetic, there are 3 types of materials that we will study today. So diamagnetic, in this case, the net magnetic moment of the atom is 0. So these are repelled, and the repulsion is not really observable. They are repelled. Now the second one is paramagnetic that you will study. So paramagnetic, the net moment of the atom is not 0, and these will be attracted. But then this attraction is at 2 different types. One is weak attraction, but there is another type of material which is ferromagnetic. Ferromagnetic is same as paramagnetic. No difference. The only difference is we'll see the domains over there. They will be strongly attracted. Right. So these are iron, cobalt, and nickel. These are the ones you make magnets of. These are the 3 materials that we are trying to study today. 3 types of materials. So we have studied diamagnetic. What happens in this case in the field? In the case of external magnetic field, they get repelled. Now let's see what happens in case of. Let's see more properties of that. So let's say you take a diamagnetic material, it is going to be repelled, right? But so that repulsion actually makes sure if there is a field in this direction, what will happen? Let's say these are the field lines, right? So you suspend a diamagnetic material, it will actually align like this. So please see this. Let me see if my webcam is visible. So this is the magnetic field lines. It is going to align like perpendicular to that. It was like this. It will align perpendicular to that. Right? And that's part of the repulsion over there. Now, if you place it in a varying magnetic field, obviously because of what we studied just now, it's going to repel. So it will go from the strong field to the weak part of it. So it will start actually moving in this direction. It will move in this direction. Is that clear to everybody? Please tell me. Nobody is replying here. Is this clear? Okay. Thanks for replying. We have covered this. I mean, I don't think we need so many slides here. We have already covered, summarized everything. So everybody, please spend like a minute or two here, go through this. And this is everything in a nutshell. Okay. Now another thing is, if you, let's say you take a watch glass, right, and you put some kind of powder that is diamagnetic here. So this is diamagnetic material. If you put like a magnetic field here, you would see actually a deflection in this case. Because think about it, there is a magnetic field here, and that magnetic field is actually repelling that. So because of that repulsion, you will see a dip in the middle of it. And when you see the paramagnetic substances, it would be like this. Okay. Now this is another behavior. Please note these down. If you're not clear, please ask me. Nobody's asking questions, so I'm assuming it is all clear. In the case of a U-tube, let's say, right, you bring in magnetic field here, it is going to be repelling this, so this will rise. So it will rise on the other side, and this will dip. Right, clear? Is this it till so far? Is it clear to everybody? Anything to be explained over again? Okay. So yeah, these things I'll cover. So some examples of diamagnetic materials are silver, water. So remember a few of them: copper, mercury. These are all diamagnetic. Now you should not expect, as I said, you bring a magnet here. Let's say this is magnet, and you bring a piece of copper. Do not expect the copper to be repelled, as in moving away. It's more like there is a repulsion, but very weak over there. It's not attraction, it's a repulsion. Now, magnetic susceptibility is low because you see it's magnetized in the opposite direction. Right? So everybody remember that, right? Magnet susceptibility is how much of magnetization is induced there. Magnetization is in the opposite direction. And that is why Xi m is low and negative. And if you remember, mu r was equal to Xi plus 1. So if this is negative, this is going to be less than 1. So mu r is going to be less than 1 for these kind of materials. Is this clear? Is it all making sense? Let me ask individually now. So Sai Kumar, yeah, is it clear to you? Okay, Rukaya, Shiba, Smita, Viraj, Aditya, Atri, Grishma. Yeah, people have been quiet today. Yeah, okay. Everybody is saying clear, and that's why you were not speaking. Rhythm, Atri. Okay, good. Abhiraj understood. Okay. Now let's go to the second type of material that we said is going to be attracting the magnetic field, right? They'll be attracted. These are paramagnetic substances. Yes, Abhiraj, you are in a bus, as always, right? So now in this case of material, what happens is there is a net magnetic moment of the atom, as you can see here. So the net magnetic moment is not equal to 0. So those electrons had some magnetic moment. They were still random over here. But when you add everything here, the total atom does not have a magnetic moment to be 0. It is some number over there. But the sample as such is still 0. So I'm going to again summarize. It may be repetition, but you really have to understand. So there was diamagnetic. In this, each electron had magnetic moment. But then when you added a magnetic moment of each electron there at the atomic level, you got 0 for each electron. Right, so you still got 0 there, right? So now we are studying paramagnetic. So paramagnetic would be more like there is an electron that has magnetic moment, right? And then you add all those up. This is not 0 for the atom, right? But then when you add up all those atoms, so we are saying, okay, let's take a sample here. There is an atom here that has magnetic moment, maybe in this direction. But then there's an atom that has magnetic moment in this direction. Somebody has in this direction, right? They all add up to 0. So so I will write it in simple words. I will not write in equation. I'll write in words here. That will be more clear. So electron has magnetic moment. Atom does not have. Right, so as at the atomic level, there is no magnetic moment, right? Now, in this case, electron has magnetic moment, right? And then, Tanya, why are you late? And you have been not attending the class. You were absent last time. Now, atom has magnetic moment, but then the sample, so sample as in the piece of sample there, right? So when you take a piece of something there, my eye is really burning. Yeah, sorry. Yeah, so then when you take a sample, it does not have. Yeah, good evening, Tanya. Like, why were you absent in past classes? Yeah, but so anyways, let's continue here. And this is what this slide is talking about. Please read this slide and let me know if this makes sense. Okay, you watched the recording. That's good then. Okay. Okay. Now, anybody who has not understood so far, please let me know. Yes, Monisha, have you understood this? Is this clear? Like magnetic moment of the atom is not 0, but when you take a collection of atoms, they're all randomized, and then that's why it is all 0. As a whole, the thing is not magnetic, right? Now let's see how they behave in external field. Yeah, what happened to my eye was actually there is some kind of infection. It is much better now. So I'm sorry, I'll keep wiping it with my cotton cloth here, but it's better than what it was over the weekend. I don't know what happened. Maybe rain or something. I don't know. Thank you for that. Yeah. So in absence of magnetic field, what happens there is this sample. So atom had some magnetic moment, right? The sample had 0 magnetic moment for the paramagnetic. Okay? But when you apply external field, sample also aligns itself, and then there is a sample magnetic field also. Okay. So this is, in short, we are talking of paramagnetic substances. This is a paramagnetic substance. There was a magnetic field in this direction, magnetic moment, sorry, in this direction. They were all randomized, right? So then total was 0. Net M was 0. But what you do in this case, let's say there is a magnetic field that you apply, and you take that material here. What would happen now is this is still randomized, but then you will see more of these are in this direction. So you can see more of these are going towards right? So there is some magnetic moment that is some develops. When you use the word some, that actually means Xi is positive and small. Right, because there is a magnetic moment developed in the direction of the magnetic field itself. Is this clear to everybody? Is this clear? Like, because remember, Xi is equal to magnetization induced per unit of this, and it's in the same direction of this, but this is very, very tiny, you can see, and that is why Xi is very tiny. And mu r, as you can see, xi plus 1, it's going to be more than 1, but very small, maybe 1.0005 or something like that. Yeah, please read this. Anything that is not clear, you're supposed to ask me immediately, please. Okay, so once you remove the field in case of diamagnetic as well as paramagnetic, you would see they all go back to all that randomized thing. So there is no dipole moment after the thing is removed. Okay, properties. We have already covered these, but this is one property. As in the case of diamagnetic, it was aligning perpendicular. In this case, it's going to align parallel to the field because it's attracted now. Okay, that's one property that's complete. And then in this case, obviously, it will behave opposite, ulta of what it was doing. So it is going to be attracted by the field. So it will move in this direction. Right? It moves from weak part of the field to the stronger part because it loves magnetic field. It's attracted, but then this attraction is very, very tiny, unnoticeable again. Please read this. Read this. Anything that is not clear, let me know. So originally it was 0. In presence, it is not 0, but very tiny. Now this is again opposite of what the behavior was for diamagnetic. Remember, it was dipping. In this case, it is raised at a height because it is attracted by that field. And this is again same thing, ulta opposite of that. It's going to rise here because it's attracted here. In that case, remember, it was dipping here and rising on the other side. Okay. So as in case of aluminium, remember. So see, again, you cannot expect these to be attracted. If you place a piece of aluminium, it is not going to be attracted to the magnet, but there is an attraction which is so small that you cannot notice it. So susceptibility is positive and small because it is a very less magnetization that is induced here. And mu r is really slightly, not really, sorry, slightly greater than 1 because it's 1 plus I m. Right? Now I'm going to pause here and ask you any confusions because I'm going to cover ferromagnetic next. I'm really going very fast, it seems, but that's okay because I'm assuming everybody is understanding. Is this clear so far, everybody? Okay. Okay, so students are saying it is clear. So ferromagnetic materials, right? So in ferromagnetic, again, let's summarize everything here. So diamagnetic, most students are clear, some students are not clear. So para, ferro. Okay, so first of all, I'll write down from the macro level what you observe. This will be repelled, slightly attracted, strongly attracted. So this will be strong attraction over there, slight attraction and repulsion. This is the behavior at the macroscopic level that you see. Right? Now behind the scenes, what happens here is each electron has the moment. So we are going from small to big, right? Atom does not have. Atom has 0 magnetic moment. Okay? And so obviously sample will also have 0. Sample as in you take a piece of this material, piece of copper, that will have 0 magnetic moment. In this case, electron has magnetic moment. Atom also has magnetic moment. Right? Now sample has 0. Sample has no, because all of them are randomly oriented and they cancel out each other. Now ferro is little different. Electron has magnetic moment. Atom has magnetic moment. Sample also has 0, but within that there are domains. Domains have magnetic moment, right? So let's see what that means. So let's say we take a ferromagnetic material. What would happen here? Let's differentiate with paramagnetic. So there is one atom here in paramagnetic which has dipole moment in this direction. Another one has this one. Another one has this one. They all are randomized, and that's why it is all 0. This is paramagnetic, right? Now if you look at ferromagnetic, things are little different. There will be pockets in here. There will be domains, and they all cooperate here. Then there's another domain here. So within a domain, they are all adding up. See, within a domain, which is roughly like 1 millimeter size, they are all adding up. But then you can see all these domains are also randomized, right? So that is why the sample, as in you take a piece of iron, they're all random domains in there. So iron is not magnetic because they are still canceling out. What would happen is this cancels out this cancels out this, everything cancels out each other, right? But if you go to the level of the domain there, oh, there is a magnet here, oh, there's another magnet here, there's another magnet here, right? So that is what ferromagnetic is. Now let's say you put in some field here. Try to understand, please. This is behind the scenes what happens. If you don't follow this, then you're going to the rectification. You'll memorize things. You will not understand what goes on, right? So what would happen is in that field, oh, there is still some randomization, but you will see more of these are oriented here in the rightward direction. So there is some magnetism induced here. In this case, look how easy and simple this would be. So there was one domain here. This was in this direction. And then there was another domain here that is also aligned now. There was third domain here that is also aligned now. They are all aligning to the magnetic field. See what happens here. Everything is aligning to the magnetic field, and that is why it becomes a strong magnet. So the examples here are this is let's say copper. This would be more like aluminium, and this is iron. Iron is ferromagnetic. You can see there is a strong magnetism develops in here. Okay. Now I'm going to pause here and ask you again, any doubts, any questions, please? No response from everybody, nobody, I mean, for past 5 minutes. No sentence here. Okay. Tanya and Sai Kumar are saying no doubt. Shibha Smita says understood. What about others? I'm really sorry, guys. This is really hurting me now. Yeah, anybody who has not understood. Atri says all clear. Abhinya, what about you? You understood, okay? Shreya, Rhythm. Okay, doubts flew away. Okay, that's good. Rhythm says, okay. Yeah, it's I'm trying to open my eye. It's not even opening. Okay. Now, ferromagnetic. So this was in a nutshell. This should cover everything that we are covering today for these three materials, right? Now, ferromagnetic substances which are strongly attracted by a magnet. So now again, understand, if this was a piece of iron, let's say this is a piece of iron, right? Within it, there are domains which are aligned there, right? So overall, this is not a magnet. But when you put a magnetic field, you're not creating a magnet. Magnets were already in there, 1 millimeter big, right? You're aligning all those magnets together. So you're not creating a magnet in the iron. Iron already has magnets, tiny little magnets inside of it. You align those magnets and it becomes a strong magnet. So please read these comments. Any comment that is not clear, let me know, please. So properties, same thing as paramagnetic, the thing will come aligned to the field, but much faster, much quickly, right? Because there is a strong attraction now. Now again, like paramagnetic, it's no different. Paramagnet have small magnetism induced, they have lot of magnetism induced. Move in this direction. Okay, Xi m is going to be positive and very high because Xi m is how much a magnetization is induced, lot of magnetization, right? And so that is why mu r is positive and very high. So let's summarize this here. If you want, you can take a screenshot of this. So let's write with some color here, maybe blue color on top. So this is negative small value, right? Mu r is between 0 and 1, right? It's in fractions, 0.7, 0.6 and all that. Now paramagnetic, it's positive small, right? And so mu r is going to be mu xi plus 1. So it's greater than 1 and very small, maybe less than 2 or maybe less than 1.1. It's tiny. It's very, very tiny. 1.35, 1. Not even 35, 1.005, something like that. This is positive and big. So mu r is going to be big. It's big. 2000, 3000, 5000, something like that. Okay. So that's what is covered here. Relative permeability is positive and very high, like 5000. Okay. So domain theory that I already covered. This is going to be more like a revision for you, obviously. So ferromagnetism can be explained on the basis of domain theory. There are a large number of small, tiny domains in there. Each domain has all these aligned in one direction. So it's useful information. Sometimes you might need it. Typically domain size is 1 millimeter and one domain has roughly of this order of atoms, 10 to the power 11 atoms, right? And they all align in one direction. So let's see, domains have irregular shape and large magnetic. Yeah, so M. Ashik has understood. We are going to move on here. So we can say atom, there is some magnetic moment in there. Domain also has it, right? So now domains are aligned, but then in a sample it will be all cancelled out unless you have an external magnetic field there, right? So let's see the behavior. We have already covered this. I don't think we have to cover this. I will actually give you a chance to ask any questions. So domains form a closed loop like structure. So magnetic moment of domain cancel out, and it doesn't show any magnetic property that we have already, in absence of electric field, right? External electric field. Now there is a field here that is applied, so these domains will actually try to align themselves in the direction of the field, and that is why you will actually have all this magnetism induced here, and that is why iron will be attracted by the magnetic field. Okay. Now all this is temperature dependent, because think about temperature means more volatility, right? So there is so much of agitation in there, they vibrate so much that randomization now increases, and that is why we already studied in previous class, as temperature increases, the magnetism or the susceptibility will reduce, right? It reduces as you increase the temperature, because temperature brings in more random behavior. And Curie temperature is where it loses all, right? So when the ferromagnetic material is heated, are all the domains in any substance perfectly balanced to cancel? Yeah, Rukaya, actually I like the question you have asked. So Rukaya has really asked a nice question. Let's talk about it. Rukaya says, are all the domains in any substance perfectly balanced to cancel out each other, right? So Rukaya and everybody, you can understand it like this. In the previous class in grade 11, you studied gases. Let's say there's a gas. Now there is a velocity, there's an atom here. That atom is going in this direction. Right? There's another atom and they're moving very fast. I mean, it's unimaginable speed. They're going very, very fast, thousands of kilometers per second. Right? So now they're moving so fast and in all possible random directions. Right? Now, can I really see all these zillion of these and see the velocities and say, oh, this one cancels out this? No, that's not possible. But think of randomization in there. Right? So if you take a dice and you roll it, you're going to get 1, maybe 5, maybe 2, right? You throw it 1,000 times, you're going to get 1/6 times, 1/6 of the time. You're going to get this 1/6 of the time, 1/6 of the time. Everything is evened out. Now instead of 1,000, may not be evened out, maybe zillion, right? Zillion. The more sample you have with randomization built in there, everything cancels out. Would you agree with that? Okay. So when the atoms are moving in random directions, yeah, everything. So net velocity here is 0. And that is the same thing when you look at the electrons here in a conductor. So free electron goes in this direction, another free goes in this direction. I don't know. Nobody can see each electron and actually measure them and do mathematics. But the rules of randomization, don't they say, oh yeah, it's going to cancel out, everything will cancel out. There is no preferred direction. So if they were going in the right direction, give me a reason for that. If there is a reason for going towards right, there is equal reason for going to the left. There's a counter reason for that. And that same logic goes in here. So when you're saying, are all the domains? Yeah, so there are so many tiny domains in there. Because of randomization, yes, everything got to cancel out each other. Do you get it now? Does that make sense? Okay. Yeah, keep asking these questions. The aeroplane is made up of duralium, and I really am struggling to read also now. If it is tried, made an electromagnet, if it is tried. So are you saying you want to make it an electromagnet out of airplane? Can you please be clear? I mean, I'm waiting. Take your time. We have enough time. So are you saying, do you want to make aeroplane as electromagnet? Why? Why do you want to make it as an electromagnet? What do you achieve by that? The question is good. No. Aluminium is not ferromagnetic, right? Aluminium is paramagnetic. Right. So there are 3 materials we studied. This is going to repel. Then we studied para, and that was going to slightly, you don't even notice. And that was aluminium falls in this bucket now. Right? And then we studied ferro. Ferro will strongly, and that is like iron, cobalt, nickel. You can make magnets out of these. Do you get it? Does that make sense? This is more like, let's say, a behavior here. You really should see this. Let's say this is a magnetic material which is diamagnetic. The field lines will be more like, oh, they're slightly repelled. You don't even notice that repulsion. This is diamagnetic. Now if you look at paramagnetic, let's write para here. Paramagnetic will be more like, oh, there's a field line that goes through, good, but then some of them are attracted from outside also maybe. But it's so unnoticeable, maybe one line in a million is bending here. Now, but if you look at ferromagnetic is huge attraction of field lines. Do you get it? It's a lot of attraction in there. So these are ferromagnetic materials, iron, cobalt, nickel. So you make magnets out of ferromagnetic materials, not paramagnetic, right? Get it? It will not act as ferromagnet. Ferromagnet is a strong magnet. Is that clear, Shibasmita? Please ask any further question if you have. Ferromagnet will be iron, cobalt, and nickel. Okay. So now Curie temperature. When magnetic material is heated, its magnetization decreases with temperature. At a particular temperature, its domain structure completely vanishes. Because there is a thermal energy actually randomizes more. It's so much of energy, you start vibrating in different directions, and then because of that your dipole moment is going to be randomized, and the thing actually loses all of magnetism. This temperature is called the Curie temperature when that happens. So and I think there was no mention of temperature here, I guess, or was it? No, there was no mention of it. No, that's the first mention. Okay. So now there was a table here I was looking for. Maybe it'll be in the coming slides. So there is a table that actually lists all these temperatures. With increase in temperature, thermal vibrations are increased, and that makes the interatomic coupling weak, because these are all linked together, and that's why they were cooperating. Let's go this way, let's go this way. All that is broken up now. Those bondings are broken up, right? Kind of like when you heat up ice, right? The bondings are broken, right? When you heat up water, the bondings are further broken to make it a steam. So domain structure is completely lost now. Now look at the temperatures, like sample temperatures. You don't have to memorize any of them, but cobalt loses at this temperature, iron loses here, nickel loses here. These are just the temperatures you don't have to memorize. But look at the high temperatures you have to heat it to make it like non-magnetic substance. It's all these ferromagnetic will convert into paramagnetic. Almost there is no domain in there now.